So chapter 1 are your fundamentals. So we're going to go through these 6 sections that are listed below. We're going to go through the topics. There are 6 topics, and here's the syllabus. Remember, it's optional. Unless you get less than a B on the test following, you'll have to redo all these homework assignments. So let's make sure we study. What's given are the formula, or the formulas that are inside of your formula sheet. Distance formula and midpoint formula are the only ones covered in chapter 1. So let's get started. We're going to start off with the real numbers. We want to define the 5 types of numbers that are listed here. Real numbers are all numbers that you can essentially think of except imaginaries. So the number 1, the number 5, the number 5 halves, 1/3, pi, root 2, e, those are all real numbers. Integers are the values, -5, -4, -3, -2, -1, 0, and so on. So they are actually the numbers that you could essentially count. Positive, negative also includes 0. Rational numbers are numbers that can be written as a quotient, which includes numbers like 5. Because that can be written as 5/1. 1/3 is considered a rational number. Something that is not considered a rational number, root 2, because you can't write root 2 as a fraction of 2 integers. Okay, and that's the thing. The quotient is made up of 2 integers. Okay, natural numbers is a special definition. Hence the little star. The definition that IB uses for your natural numbers are your natural counting numbers, which usually would be 1, 2, 3, 4, 5, and so on. Gets their name natural, meaning how you would count, but IB adds in the value 0. So it's actually your positive integers added with the value 0. Irrational numbers are the numbers that are not rational. And the ones that are not rational would be things like root 2, can't be written as a fraction. Pi can't be written as a fraction. E cannot be written as a fraction. So these are the type of definitions that you will need to know. I'm going to do a quick Venn diagram. So if this whole entire screen is considered the real numbers, so we're not talking about imaginaries. So those are the real numbers, and then within the set of real numbers, we have the rational numbers. Let's see. So if this whole screen are the real numbers, then actually let's draw a nice little box here for my Venn diagram. All right. So then we can actually split up and say that this portion here would be considered our irrational numbers. This side here would be considered our rational numbers. Okay? And both together would make our real numbers. Now, within our rational numbers, which is this entire box to the right. So within the rational numbers, we get that we may have inside of the rational numbers this group of numbers that are called our integers. And then within our integers, we have the natural numbers. All right, so natural numbers start at 0, count up 1, 2, 3, 4. The natural number symbol is a thick N in a sense. And then the integers symbol is a thick Z. And the integers would be -1, 0, 1, 2, and so on. Rational numbers are numbers that can be written in the form of P divided by Q. I should have mentioned that Q cannot equal 0. And so rational numbers, 1/3, 5, 2/9. Irrational numbers, root of 2, E, pi, and then all the numbers written on the board are considered real numbers. I believe that I forgot to mention the symbol for real numbers, which is the thick R, and the symbol for irrational numbers is Q. All right, so moving on, we have set notation. I think the only thing that I really want to go over with you are this guy, and this guy. So let's do set A has the numbers 1, 2, 5. Set B has the numbers 1, 2, 5, and 6. So what you'll notice is that set A is considered a subset of B. So this symbol here is a subset. When you have that every single element is actually in, so if I had another set C that was also 1, 2, and 5, then I would say that set A is within and equal to set C, and I would actually also say that set C is within and equal to set A. That's kind of our way of saying that the sets are actually equal to each other. And then this last one here that kind of looks like a rounded E, so that would be if I do something like X and then I put the symbol for real numbers, it's saying that X is an element of the real numbers. And you'll see in your book, they'll say things like the natural numbers is a subset of the integers. Okay? Or is an element of. All right, moving on. We have absolute value. So the definition of absolute value is essentially a distance. And remember that distance must be positive. So the definition for the absolute value of A would be that when it's positive, it's just the value itself, and when it's negative, that happens when A is less than 0. And the equals is kind of optional because 0 doesn't have a sign. So you'll more so see something like this, x minus 2 is equal to 5, let's say, or that's not a 5. What this says is the distance from 2 is 5. And the reason we call it a distance is if the number 2 is here, the distance means that I could actually hop forward 5 units, 1, 2, 3, 4, 5, and I get to 7. Or I could go backwards 1, 2, 3, 4, 5, and get to -3, and those both would be the answer. To solve absolute value, we actually set the equation equal to itself, and then we also set it equal to the negative value. So roots and radicals. So your book uses the word surd, which you probably have not seen. Surd is the same thing as a radical. A radical is the root symbol. So it could be the principal square root, which is just squared root, third root, and so on. Simplifying roots, you just have to remember, if I wanted to find the, say, square root of 20, if you want to simplify it, we know that the square root of 20 is not going to be a perfect square root. Therefore, 4 times 5, 2 times 2. Therefore, this is a pair, comes outside. Whoever does not have a pair stays inside. If you wanted to do a little bit harder one, example here would be the third root of 40, let's say. So 40 would be 4 and 10. It would be 2 and 2. 10 would be 2 and 5. Since it's a third root, you need 3 of them to come outside, and whoever's left over would have a third root. Some Exponents and indices 1.3. So we're moving quickly here. When we are talking about, actually, let me back up a little bit. I'm going to insert a page here because for your square root problems, let's just make sure that there's some basic things to remember. So if I had a problem such as, so example 3, the square root of 12 plus 8 square root of 3. You can't add them unless the roots themselves are the same, and I'm sure you all know that. So we do 4 times 3, that's 2 times 2. So that's 2 root 3 plus 8 root 3. And now because the root 3's are the same, we can add them together and get 10 root 3. Otherwise, we could not add until the roots were the same value. Now back to exponents and indices. I'm going to assume that you know most of your exponent rules. Let's just talk about things such as part A here, 2xy squared cubed. So when you have a power to a power, so where did that happen? First of all, this power on the outside should get distributed 3 times. So I get 2 cubed, x cubed, y squared cubed. When you have a power to a power, which is right here, we multiply. So we get 2 cubed, x cubed, y to the 6. Which would be different than if I was going to do a, let's see, x to the 5th times x to the 6th. Here's where we add our power, so that would give us x to the 11th and not x to the 30th. There are a few other rules in here. Letter D, anything to the 0 power, doesn't matter what it is 1. Remember that letter C here has a -3 exponent, so what we can do is move the -2 to the bottom and then cube it. So the negative just means switch its location. If it's a denominator, move it to a numerator. If it's a numerator, move it to the denominator. So this answer would be 1 over -8. I would say the only other thing that I would want to do is letter J for you. You have the root of a plus b over a plus b. There are multiple ways to simplify this, but we're going to just use exponents. The root is the same thing as a 1/2 power. When there is no power, it's the same as a 1 power. So you could do the subtraction rule, which is top minus bottom, or numerator power divided by, subtracting denominator power, or we can just say who has more. The bottom has more powers by how many? By 1/2. All right, moving on. 1.4, scientific notation. So the major thing about scientific notation is understanding that the value in front, the A value, must be between 1 and 10. So it has to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cannot be used. So 10, notice there is no equal sign. K has to be an integer. So A is allowed to be a real number, usually a decimal, and then the K, which is the power of 10, has to be an integer, so positive or negative counting numbers, including 0. So if you see here letter A, the reason why I'm doing these is because it also takes care of multiplying and dividing. So 64 would be written as 6.4 times 10 to the 1, 2, 3, 4, multiplied by 2.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. And what's nice about multiplying in scientific notation is you can put your 6.4 in front, multiply by 2.5, multiply by 10 to the 4th, multiply by 10 to the 9th. So what that takes care of is having to multiply the 10 to the 4th and 10 to the 9th. Same base, it's just 10. The power is now 13 because we're going to add the powers. And up here, you would just multiply 6.4 times 2.5, and you'll actually have your value in scientific notation, which is 16 times 10 to the 13th. But since 16 is bigger than 10, we'd have to turn it into 1.6, and then this would become 10 to the 14th because I moved the decimal 1 to the left, which caused me to have to raise the power by 1. Division is very similar. Division, I would write letter B. So letter B has you dealing with values that are smaller than 1. So letter B, I would have 7.8 times 1, 2, 3, 4, 5, 6, 7. So times 10 to the negative 7 divided by 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.2 times 10 to the negative 9. So this deals with the negative powers. The 7.8 and the 1.2, we don't have to worry about. We're just going to divide those. And we can really deal with taking your 10 power and doing negative 7 minus the negative 9. So we have 7.8 divided by 1.2 times 10 to the second power. So we end up with 6.5 times 10 to the second power. So there's your scientific notation. So just remember that this value up here can only be between 1 and less than 10. This must be an integer when you're all done. All right, algebraic expressions. So a polynomial, a lot of you need to see the definition. A polynomial in the variable x, given that you have all these a values in the real numbers, where a of n is not equal to 0, and the n's are in the positive integers. That's what this says. That's new notation, also z with a little plus. A polynomial in x is a sum of distinct terms in the form. So most of you should know. The thing that I wanted to point out is understanding that the power of n, so a x to the n, this must be a positive integer. So it cannot be a root, a third. Okay? So in this section, we really talk about factoring versus expanding. I put the definition of a polynomial so that you understand that the root of x is not considered a polynomial. X to the 2/3 is not a polynomial. So these are not polynomial functions. Okay? Remember that the degree is always the highest power. All right, so we're going to move into factoring and expanding. So expanding is the easy thing where you're just asked to multiply through. The only thing I really wanted to mention was part E, making sure you understand that if you have a third power, that you are really multiplying by itself 3 times. That's what powers do. Okay? Make sure that you understand how to do problems like part F, which I will do with you here. 3 plus 2 root 5 times 3 minus 2 root 5. So most of you guys will call it foiling. I call it distributing. So I'm going to distribute the 3 to the 3, and then this 3 to the negative 2 root 5. So I get 3 times 3, which is 9. 3 times negative 2 root 5 would be negative 6 root 5. And then I'm going to go underneath here and do the 2 root 5 multiplied by 3, which is 6 root 5. And then 2 root 5 multiplied by negative 2 root 5, and I get negative 4 times 5. So we end up with, we knew that was going to happen, hopefully. We have 9 minus 20, and so we get negative 11 as our answer for this guy. This one here is called a difference of squares. That's where it comes from. So moving on, factorizing, the types of factoring that you really should make sure you know. GCF factoring, factoring out a GCF. GCF by grouping. You should be able to factor any kind of trinomial, which includes specials, sum, actually not sum, sorry, difference of squares. Squares, which would be things like in the form a squared minus b squared. And then you should be able to factor a few cubic functions, which would be a cubed plus b cubed, and then also factor a cubed minus b cubed. Okay. I put a little note here that says always factor by GCF first. Greatest common factor must always be checked for first. So my guess is from the list that I gave you, the only thing you might not remember is a cubed plus b cubed. You do have to have this memorized, so I always do that the first factor looks the same. Okay? We'll do a cubed minus b cubed at the exact same time. So the first factor always looks the same. So then I move into a squared, ab, b squared. And this part, same thing. A squared, ab, b squared. The pattern that I notice is that both of them have to have a negative sign. So if the first one has already the plus, it needs a negative, so the next one will have the minus sign. And then since we already have our one and only minus sign, I'm done. The second one already has its minus sign, therefore the other ones are both plus. That's how I memorize them. I have a hard time memorizing those. So moving on. We want to completely factor these. I am going to go through probably A, B, C, and E. So let's start with A. 2x squared minus 14x plus 24. Since they're all even, it means that I should be able to factor out a 2, which leaves me x squared minus 7x plus 12. And I need two numbers that multiply to this number, but they're going to add up to this number. And the two numbers, oopsie, let me keep going over here, would be x minus 4 and x minus 3. And if you multiply back out, distribute, you'll get your original question back again. Part B, 2x squared plus x minus 15, no GCF. So what I'm really looking at are two factors where the front values here will multiply to 2x squared. So I know one of them has to be a 2x, the other one has to be an x. In the back, the terms must multiply to negative 15. So we can just guess and try, say, 3 and 5. And then how do I know which one's positive and which one's negative? Because I got to make it multiply to negative 15. I am actually going to multiply here and multiply here, but then add. So what do I mean by that? If I decide to put the negative here and put the positive here, I would end up with, in the middle, 5x. And then from this guy, I would end up with negative 6x. And if you add them, I get negative x. That tells me that that does not match this guy. So I'm going to erase this guy and try again. And hopefully this time, because I knew I wanted positive x and I got negative x, all I'm going to do is switch the signs. And what you'll notice is you get negative 5x here, you get positive 6x here, and they add up to positive x, which is exactly what we wanted. So they are my factors. So that is part B. And now we're on part C. Let's try to put that here, save a little space. 4x to the 6 minus 9. So what I'm looking at is this is a perfect square, meaning 3 squared gives me that value of 9. Over here is also a perfect square. Something squared will give me 4x to the 6. So the value in the front is easy. That's 2. 2 squared gives me 4. X to what power squared would give me 6? Well, x cubed. So x cubed, if I squared that, I would get x to the 6th power. So the type of factoring this is the difference of squares. So in the front, I'm going to write exactly what I had, 2x cubed, and in the back, I'm going to put a 3 and a 3, and one of them is going to be a plus, and one of them will be a minus. All right, last one is letter E, which is similar to what I just had a second ago. So here, it's actually already written for you. This squared, this squared. So all I'm going to do is put 1 plus, 1 minus. The front would be x plus 3. And in the back, I will put my y and my y. If you multiply it back out, you'll notice that it does equal what we had a second ago. Simplifying algebraic fractions. So here's where we do get some more complicated problems. So I will do each of these for you. So part A, on top in the numerator, I'm going to factor out the GCF. So I have 2 and an A. So the first term I have an A left over, and in the second term, I have the b left over. In the bottom, I'm going to factor out a 6, an a, and a b. And what do we have left over in the front term? Nothing, so I put a 1. And in the second term, oh lordy, made a little mistake right here. A cannot be factored out. So, whoopsie. So what we get here in front is that 6 can be factored out and b can be factored out, but not the a. So in the front term, I have an a left over. In the back term, I actually have a b left over. So, and we get a over 3b. Letter B. Factor the top, 1 minus x, 1 plus x. Factor the bottom. I know the front term has to be x. The last terms have to multiply to -2, but add up to 1. So I know one of these will be a 2, one of them will be a 1, and I want to add up to a positive 1. So this must be the positive, this one is the negative. What you'll notice, let's see, this term and this term are not exactly the same. They actually don't cancel at the current moment. What I am going to do is I'm going to factor out a -1 from the front term up in the numerator. So if I do that, the x becomes positive, the 1 becomes negative. In the denominator, I'm leaving it alone. I haven't done anything to the denominator. What you'll notice is now they factor and I get left with -1 plus x divided by x plus 2. Third problem should look familiar for those of you that took calculus, which I believe are all of you. X plus h squared minus x squared all over h. You could actually distribute this and you'll get the right answer, but I'm going to do this factoring because we just came from the factoring section. So this term would be my a term, this would be my b term, and we're going to use the factoring of a minus b, a plus b, because they're both squared. So really, I'm going to do x plus h in the front, x plus h in the front. One of them will be a plus, one of them will be a minus, and in the back, I'm going to use this x right here. So I put an x here and an x here, all divided by h. You will notice that in this term, those cancel, and I get 2x plus h from the first set of parentheses. The second factor is just an h divided by h, and we get left with 2x plus h. All right. Moving on, let's see what we got next. Adding or subtracting fractions. So I'm not going to do all of these. What I will make sure that you understand is anytime you have algebraic fractions, you must get a common denominator. And so the one that I will do is part C with you. Part C, that's your first term. The second term I'm actually going to factor. I can't pull out a GCF because the x term does not have a coefficient, so it should be factorable. Let's hope it is. It makes the problem much easier. I know in the front, if it's factorable, would have to be a 2. I need to find two numbers in the back that will multiply to -6 but add up, when I do this type of adding, to +1. And so in my mind, I'm thinking that I would use 2 and 3. So 2 would go here, 3 would go here. I want positive x, so this would make 4. So I'm going to make that positive, make that negative. Therefore, I have -3x plus 4x, which gives me a +1x. Let's erase this guy. And so what we'll notice is the only term that's missing from the first is this. So here's my common denominator. You'll notice that this is the same as this. So I'm just going to write the whole thing with a common denominator of 2x minus 3 times x plus 2. And in the numerator, I have 4x minus 6 minus x minus 4. Please make sure you note the parentheses. That is because I'm subtracting the second fraction right here, which means I'm subtracting this whole thing. So what do we get left with? We get left with 4x minus x is 3x. So really what I'm doing is distributing the negative. So I get 4x minus x, and then I get -6 plus 4, which gives me -2. And on bottom I have 2x minus 3 and x plus 2. So the denominator still has my two terms. Nothing can be simplified any further, and we're going to leave it factored. Okay? Let's see. Simplifying each compound fraction. So it looks as though these are a little bit more complicated. And compound fractions is what I called a stacked fraction. A fraction on top of a fraction. You'll hear me say stacked fraction often. And I say never, never let yourself have a stacked fraction. Essentially, if you ever have a stacked fraction, you want to create one complete fraction in numerator or denominator. So what I mean by complete, this part right here is not a complete fraction. It's two fractions that are being added or subtracted. So let's do part A. What I would do is get a common denominator, which would be, and I'll write it right now what it's going to be, x plus h times x. In the first term, I would have to multiply by x over x. In the second term, I'd have to multiply by x plus h over x plus h. So in the numerator, I get x. In the second term, I get negative x, negative h. The denominator was x plus h times x, and then the whole entire thing was divided by h. So instead of writing divided by h, instead, I'm going to write multiplied by 1 over h. Anytime you divide by a number, you can multiply by its reciprocal. So what do we end up with here? We get negative h over x plus h times x times h, and we get negative 1 over x plus h times x. All right, letter B, in my opinion, is very similar. Letter C is a little interesting. So letter C, not exactly sure what way they would go about doing this one, but I would say I'm going to start off by writing it without the negative 3/2 power. So I'm going to write this as a 3/2 power plus 1 over 1 minus 2x to the 1/2 power, and the whole thing over 1 minus x. So if you look at the numerator, which would be this part, I'm going to try to get a common denominator. So if you look at it, really, I just need to multiply this one by 1 minus 2x, 1 minus 2x to the 1 power, which is the same as 2 over 2. So 1/2 plus 2 over 2 would give me the 3/2 power. That is over here. So I have x plus 1 times 1 minus 2x all over 1 minus 2x to the 3/2 power. And instead of dividing by 1 over x, I'm going to multiply by 1 over 1 minus x. So what do we get left with? Let's see. So in the numerator, I have x plus 1 minus 2x all over 1 minus 2x to the 3/2 times 1 minus x. And it looks like we have up in the numerator negative x plus 1 over 1 minus 2x to the 3/2, which, oh, forgot one little piece down here. 1 minus x, which cancels that guy, and we get left with a much simpler fraction. There you go. So that would be how you want to simplify your compound fractions. I thought C, when you first look at it, was hard to figure out exactly what to do, but I would write it without the negative fractions, therefore being able to get the common denominator. Moving on, rationalizing the denominator. You all probably do remember doing this at one point, but you multiply by the conjugate. So I get 2 times 1 minus root of 5 over 1 plus root of 5. I'm writing it bigger so you can see it a little better. The numerator, you just get 2 minus 2 root 5. The denominator, you're going to FOIL, but remember that that is now in the form of a plus b, a minus b, which means that you can just write it as a squared minus b squared. So I'm going to write it as 1 squared minus root 5, whole thing squared. And we get 2 minus 2 root 5 over 1 minus 5. We get 2 minus 2 root 5 over negative 4. And depending on how you want this written, if I want it written more so like complex numbers, a plus bi, or a plus b root, I could separate the fractions and get this value. Either of the two. Or I could divide every value by 1, or sorry, by 2, and get this. Either value would be correct. All right, equation of a line. You have a total of 5 here for you. General form is a form that you're probably not used to, but you should know how to notice that that's a line. So that's the first one. This is probably the one that you remember from Algebra 1. Algebra 2. Then pre-cal and calculus, you use point slope. Horizontal lines are always in the form y equals. Vertical lines are always in the form x equals. Things to remember: the slope is 0 for a horizontal line. The slope is undefined for a vertical line. So I have one example. Find the equation of a line that passes through the point. So this would be your x1, your y1, and has a slope of 12. So y minus 31 is equal to the slope times x minus 3. So that's point slope form. But it says right in the equation slope intercept. So we're just going to simplify what we have here, which would be 12x minus 36. And then we're going to add 31 to both sides. And we end up with y is equal to 12x minus 5. So this is our slope. This is our y-intercept, which doesn't really show up in the point slope form. The only thing that does show up is the 12, which is your slope. But the negative 5, you really do need to solve for to find the y-intercept. Last set, I think, of problems. There's the distance formula, the midpoint formula. So I gave you some definitions that you should know. A scalene triangle has 3 sides, all different lengths. Pretty much what you do, you use the distance formula between the points. And you want to show that all 3 distances are different. An isosceles triangle, 2 sides are equal. So for that one, same thing. You want to use the distance formula to just show that 2 sides are equal in distance. Equilateral, all sides equal. So you should know that that is also a distance formula. A right triangle has a 90-degree angle. So here you would use slope. And you want your slopes to be perpendicular, opposite reciprocals. So actually, let's write that a little bit neater here. Slopes perpendicular means opposite reciprocals. And then the last one, a parallelogram, would be 2 sets of parallel lines, which would be opposite sides have same slope. So you don't really need the midpoint in any of these, but the midpoint formula is given in this section. You should be able to identify any of those shapes using the distance formula or slopes. The parallelogram you really could do in a different method. You could actually find that the opposite sides are equal, so you could do the distance formula. I find slope to be much easier than the distance formula. The last section that you have is solving systems of equations. They show you how to find it graphically. That should make sense to you guys. Solve for y, set them equal to each other. Elimination you haven't done in a while, so we'll look at both of these. Elimination essentially says that you want to multiply full equations by a constant to see if you can add or subtract to eliminate a variable. So looking at part A, I would multiply this one probably by 2 and this one by -5. What that does for me, I get 10x plus 6y equals 18. I get -10x plus 20y equals, let's see if I can do this, -70. And then you would add these, because if I add them, I would cancel that. I get 26y is equal to -52, hopefully. And therefore, I get y is equal to -2. And then the x value you can substitute back in to find. Substitution is definitely the more common method. I think it's the method that you really should make sure you know. Substitution says whenever you're given more than one equation, take one of the two equations, and in this case, I'm going to take the easier one, and solve for a variable. The easiest variable to solve for will be y. So I'm going to move y to this side, which would make it positive, and then I'm going to add 9 to the other side. So there's my y value. And then all I'm going to do with my y value is I'm going to substitute it into 6x plus 2y, which is the other equation, equals 2. So 6x plus 2 times 3x plus 9 equals 2, and I get 6x plus 6x plus 18 equals 2. 12x is equal to negative 16. X is equal to negative 4 over 3, if I did that right. Sometimes I make dumb little mistakes I don't even notice. And I want to say that that is everything from chapter 1. So again, if you don't feel like you need to practice all the problems, you really don't have to, but you have to guarantee that you know enough to be able to get an A or a B on the upcoming test. Thanks, guys.